On July 9th, 1962, the United States launched a 1.4 megaton thermonuclear warhead 250 miles above the Pacific Ocean and detonated it in outer space. The explosion was 100 times more powerful than Hiroshima. What happened next wasn't just unexpected. It knocked out streetlights in Hawaii 900 miles away, crippled a third of all satellites in orbit, and created an artificial radiation belt around Earth that lasted for years. The scientists who designed this test had run their calculations, built their models, and signed off on the detonation. They were some of the brightest minds in nuclear physics. And when that warhead went off, it broke every single assumption they had made. This is the story of Starfish Prime, and why its consequences mean we can never do it again. To understand why America decided to detonate a nuclear weapon in space, we need to go back 5 years earlier, to October 4th, 1957. That's the day the Soviet Union launched Sputnik, the first artificial satellite. Now, the threat wasn't the satellite itself. It was what launching it proved. The Soviets had a rocket powerful enough to carry a nuclear warhead to any American city in under 30 minutes. That realization sent Washington into something close to panic. The space race gets remembered as a competition about exploration and putting men on the moon. But at its core, it was a military problem. Whoever controlled space controlled everything beneath it. The question facing American defense planners was straightforward but terrifying. If the Soviets can put things into space, what exactly can they do from up there? And more importantly, how do we stop them? Subscribe to Space Aquarius and let's begin. That's where a self-taught physicist named Nicholas Christopoulos enters the picture. This guy had learned nuclear theory while working as an elevator repairman in wartime Greece. He understood something crucial about Earth's magnetic field, the invisible shield generated by liquid iron moving in our planet's outer core, that extends from the surface out into deep space. Christopoulos had an idea that seemed almost too clever. Earth's magnetic field traps charged particles and holds them in what we call the Van Allen belts, named after physicist James Van Allen, who discovered them using data from America's Explorer 1 satellite. Here's what Christopoulos theorized. If you detonate a nuclear weapon at high altitude inside that magnetic field, the explosion releases a massive burst of high-energy electrons. The magnetic field catches those electrons and traps them just like it traps natural radiation. You'd be creating an artificial radiation belt, a man-made ring of charged particles circling the entire planet. And here's the genius part. A belt of energized electrons positioned correctly would be lethal to the electronics of any Soviet ballistic missile flying through it. See? Intercontinental ballistic missiles don't fly across the ocean like aircraft. They go up through the atmosphere, arc through space, then come back down. A radiation belt in the right orbital slot would fry their guidance systems before they ever reached their targets. The Pentagon moved on this immediately. In the summer of 1958, less than a year after Sputnik, the US Navy secretly dispatched 9 ships to the South Atlantic. This was Operation Argus. 3 nuclear detonations at altitudes between 125 and 335 miles, designed to test whether artificial radiation belts were actually achievable. The belts formed. Christofoulos's physics was correct. The electrons spread along the magnetic field lines exactly as theorized, and instruments picked up a measurable radiation increase in the targeted orbital band. But there was a problem. The belts dissipated too quickly to be militarily useful. They faded in days, not the weeks or months needed for an effective missile defense. Still, the concept was proven, and that set the stage for what came next, something much bigger. By 1962, the United States began to scale up. The program was called Operation Fishbowl, run out of Johnston Atoll, a flat strip of coral 930 miles southwest of Hawaii, chosen because it was as close to the middle of nowhere as geography allows. The first attempt came on June 2, 1962. A warhead mounted on a Thor rocket launched just after midnight. The missile was immediately lost on radar. Think about that for a second. They had launched a nuclear weapon into space and didn't know where it was. The flight termination system destroyed it remotely. Debris went into the ocean. Then came the second attempt on June 19th. Another Thor rocket. This time the engine failed at roughly 30,000 feet, and the missile broke apart, scattering plutonium-contaminated debris across Johnston Island and the surrounding water. Cleanup crews spent 2 weeks recovering radioactive fragments from the lagoon. Then there was the third attempt, July 9th, 1962. This one worked. The Thor missile carried its 1.4 megaton thermonuclear warhead all the way to 250 miles altitude, roughly the orbital height where the International Space Station flies today, before the warhead detonated successfully. This was Starfish Prime, the largest nuclear test ever conducted in outer space. A nuclear explosion in space looks nothing like what you'd picture. There's no mushroom cloud because there's no dirt to pull into the air. No fireball because there's no oxygen to burn. What there is an intensely bright flash that expands outward in a perfect sphere, edges breaking into short, curling tendrils as the energy dissipates. Then, the auroras start. Ionized particles from the detonation hit the upper atmosphere and produced auroras across a vast region of the Pacific. They were visible from New Zealand, 4,350 miles away. In Honolulu, the sky lit up and stayed lit for 6 minutes. It was 11 p.m. local time, and suddenly it looked like dawn. Radio links failed. Streetlights went dark. Burglar alarms triggered across the island. Hotels in Honolulu had actually advertised rooftop viewing parties with headlines reading, "Nuclear blast tonight may be dazzling." They weren't wrong about that part, but the auroras were expected. Everything else was not. When a nuclear weapon detonates, it releases gamma rays in all directions. Those gamma rays hit the upper atmosphere, collide with air molecules, and knock electrons loose, a process called Compton scattering. At 250 miles altitude, where the atmosphere is extremely thin, those freed electrons travel large distances before hitting anything. Earth's magnetic field then accelerates them into a rapid oscillation of electromagnetic fields. That's the electromagnetic pulse, the EMP. At high altitude, with almost nothing to absorb it, the pulse spreads laterally across an enormous area. The models had predicted a significant EMP. What was actually recorded, before most instruments were driven completely off the scale, was something orders of magnitude beyond those predictions. The measurement equipment simply couldn't capture the numbers. In Hawaii, 930 miles from the detonation, 300 streetlights went out simultaneously. A telephone company microwave link was damaged, shutting down calls from Kauai to the other Hawaiian islands. The EMP had traveled nearly 1,000 miles and still had enough power to knock out infrastructure. But the EMP wasn't the part that worried scientists the most. The radiation belt was. Starfish Prime injected a massive quantity of high-energy electrons directly into Earth's magnetosphere. The magnetic field did exactly what the Christofilos research had predicted it would do. It caught them and held them. An artificial radiation belt formed around Earth, layered inside the natural Van Allen belts. And it was more intense than anything the models had projected. Glenn Seaborg, who was chairman of the Atomic Energy Commission and a Nobel Prize winner in chemistry, later wrote that the Starfish results contravened all our predictions, and that the intensity of the new belt far exceeded anything the scientific community had anticipated. The belt didn't dissipate in days or weeks. It persisted for years. Electrons from the Starfish detonation were still being measured in the atmosphere in 1968, 5 years later. In 1962, there were roughly 24 operational satellites in orbit. All of them were now flying through an artificial radiation environment nobody had planned for. Telstar 1, which had just relayed the first live transatlantic television broadcast in history, went silent within 7 months. Its transistors had been damaged by the radiation. Ariel 1, Britain's first satellite, was rendered inoperable within weeks. Meanwhile, the Soviets ran their own high-altitude tests over Kazakhstan that same October, injecting more electrons that merged with the Starfish belt and intensified it further. By the end of 1963, at least 6 satellites had failed as a direct result. That was roughly a quarter of everything humanity had put into orbit. James Van Allen himself, the man whose name is on the radiation belts, had publicly stated before the test that Starfish Prime would not meaningfully disturb them. He was wrong. That same year, 1963, the United States, United Kingdom, and USSR signed the Limited Nuclear Test Ban Treaty, prohibiting nuclear tests in the atmosphere, in space, and underwater. Just months after the Cuban Missile Crisis, the superpowers agreed no more nuclear explosions in space. The Outer Space Treaty followed in 1967, banning nuclear weapons in orbit entirely. The Soviet Union never came clean about their own high-altitude tests. 18 R-36 orb weapons, designed to bypass American early warning radars by coming over the South Pole, were based in silos near Tyuratam. They were later banned by the SALT II Arms Control Treaty. The weapons had long since been obsolete anyway, foiled by new American radars and Soviet ballistic missile submarines. In 1962, there were 24 satellites in orbit. Today, there are approximately 11,000 and counting. GPS, weather systems, financial infrastructure, communications, navigation. The systems modern civilization runs on all have a satellite somewhere in the chain. Most are not radiation hardened. A Starfish-scale event today would not just damage satellites in the blast zone. It would create a radiation environment degrading every satellite passing through that orbital band for years. Satellites that fail don't disappear. They become uncontrolled debris at orbital velocity, generating collisions, generating more debris. This is called Kessler syndrome, a cascade of collisions that could make certain orbits unusable for generations. Earlier this year, Russia vetoed a UN resolution against putting nuclear weapons in space. According to John Plum, Assistant Defense Secretary for U.S. Space Policy, Russia is developing a concerning anti-satellite capability, a new satellite carrying a nuclear device. This would violate the 1967 Outer Space Treaty, which has no formal enforcement mechanisms. The lessons of Starfish Prime are more relevant than ever. On that night, in July 1962, the The sky over the Pacific lit up with an artificial aurora that stretched for thousands of miles. It was beautiful. It was terrifying. And it was a warning. We learned that space is not empty. It's not a void where we can do whatever we want without consequences. It's an environment we barely understand, and one we depend on more every single day. Starfish Prime showed us what happens when we detonate a nuclear weapon in space. The answer is nothing good, and we can never afford to forget it. If you enjoyed this deep dive into one of the most consequential experiments in space history, hit that like button. Subscribe to Space Aquarius for more stories about humanity's greatest achievements and biggest mistakes beyond Earth. Drop a comment below telling me what space topic you want covered next, and share this video with someone who loves Cold War history or space exploration.